Somewhere over the English Channel, February 1944. A B-17 from the 351st Bomb Group took a direct flak burst through the fuselage at 22,000 feet. The shell didn't kill anyone outright, it did something slower. It opened the belly of the aircraft, shredded the hydraulics, and put 5 men down in pools of their own blood before the plane crossed back over the coast of England. The ball turret gunner, Corporal James Everett Wilder, 20 years old, from Macon, Georgia, had worked in his father's hardware store before the draft took him. He had never seen the inside of a hospital. He had no medical training. When the top turret gunner above him stopped moving, Wilder crawled out of his turret and did the only thing the army had taught him to do. He opened a small cardboard box from the emergency kit mounted to the bulkhead. Inside was a tin of yellowish powder and a printed card with 6 steps on it. He followed the steps. He mixed the powder with sterile water from a separate vial. He shook the bottle for 30 seconds. He ran a rubber tube from the bottle to the needle, found a vein, and pushed the contents into a man who had lost somewhere between 1 litre and 1.5 litres of blood at altitude. The man lived. When they landed at Polbrook and German prisoners were brought through the medical station later that week, standard intelligence processing, one of them, a field surgeon from the Luftwaffe, was shown the kit. He held the tin of powder and turned it over in his hands for a long time. Then he asked, through an interpreter, the same question that German physicians had been asking in captured documents and interrogation reports since the summer of 1942. He asked, "How is this possible?" That question, 3 words from a trained physician holding a tin of dried plasma in a British airfield, is the centre of this investigation, because the answer isn't simple. The answer reaches back to the 1930s, to a laboratory in Chicago, to a man named Charles Richard Drew, and to one of the most consequential decisions in the history of military medicine. A decision that saved somewhere between 200,000 and 400,000 Allied lives, depending on which post-war analysis you trust. To understand why that German surgeon couldn't believe what he was holding, we need to go back to the beginning. Not the beginning of the war, the beginning of blood itself as a problem. The problem with blood. For most of human history, blood was understood to be irreplaceable. If you lost too much of it, you died. That was the end of the analysis. Surgeons from Galen to Ambroise Paré to the Napoleonic field hospitals operated under the same fundamental constraint. Once a man bled out, no human intervention could reverse the process. You could slow the bleeding, you could close the wound, but you could not give back what was gone. The first serious attempt to change this came in the 1600s when a physician named Richard Lower, working in Oxford, successfully transfused blood between 2 dogs. He kept one dog alive by connecting its jugular vein to the carotid artery of another. The experiment worked in a narrow technical sense. Then, in 1667, a French physician named Jean-Baptiste Denis tried the same procedure on a human patient, transfusing sheep's blood into a boy who had been bled repeatedly as a treatment for fever. The boy survived. Denis tried again with a second patient. The patient died. The problem, which Denis could not have named but which killed his patient, was incompatibility. Blood is not a uniform substance, it is a system, and systems built for one organism are not automatically compatible with another. That knowledge, the actual biochemical knowledge, would not arrive for 2.5 centuries. In 1901, an Austrian physician named Karl Landsteiner, working at the Vienna Pathological Institute, published a paper describing what he had found when he mixed blood samples from different people. Some combinations clotted, some did not. He identified 3 groups, A, B, and C, which later became O, and established the fundamental principle that would make transfusion medicine possible. Blood types exist. They are heritable, and mixing the wrong types kills the recipient. Landsteiner won the Nobel Prize for this work in 1930. By that point, the military implications had already been demonstrated once, under catastrophic conditions. In the First World War, between 1914 and 1918, military surgeons on both sides watched men die of hemorrhagic shock, the state the body enters when blood loss exceeds roughly 30% of total volume. The heart begins to race, blood pressure drops. The organs, starved of oxygen, begin to fail in sequence. Kidneys first, then the gut, then the brain. The process, without intervention, takes between 1 and 6 hours, depending on the rate of loss. By 1917, the British and Canadian armies had begun performing direct transfusions in forward areas, matching donors to recipients by blood type. The results were striking. A Canadian physician named Lawrence Bruce Robertson, 28 years old, from Toronto, trained at the University of Toronto Medical School, documented 14 consecutive transfusion cases in 1917, all of which survived injuries that would previously have been fatal. He published the results in the British Medical Journal. The paper reached military medical authorities on both sides. A direct transfusion had a problem that Robertson's paper could not solve. It required a living donor. The donor had to be present, typed, and physically connected to the patient. In a forward surgical station, under artillery fire, with 5 men bleeding simultaneously, finding a compatible donor and running a direct transfusion was not a logistical reality. It was a laboratory procedure performed in a war zone. The alternative, storing blood in advance, seemed obvious. But blood, as anyone who has left a cut on their hand discovered, does not keep well. It breaks down. Red cells rupture, proteins denature, bacteria colonize. In 1917, the longest anyone had managed to store whole blood was 6 days, using sodium citrate as a preservative under refrigeration. 6 days, refrigerated, in a war where the front lines moved daily and refrigeration was a luxury. The problem sat there, unsolved, for 20 years. And then, in the 1930s, 2 things happened simultaneously on different sides of the Atlantic that would eventually collide in a tin of yellow powder held by a Luftwaffe surgeon at a British airfield in 1944. The first thing was Spain. In the Spanish Civil War between 1936 and 1939, a Canadian physician named Norman Bethune, 46 years old, born in Gravenhurst, Ontario, a thoracic surgeon who had previously contracted and survived tuberculosis, set up the world's first mobile blood transfusion service. He drove a refrigerated truck to the front lines of the Republican forces, carrying stored blood collected from civilian donors in Barcelona. The blood was typed, bottled, and kept at 4 degrees Celsius. Bethune's service delivered roughly 1,000 transfusions over the course of the war. It worked. The survival rates were documented. The concept of blood banking, collecting blood in advance, storing it, transporting it to the point of need, was proven in combat conditions for the first time in history. The second thing was Chicago. In 1936, a physician named Bernard Fantus, working at Cook County Hospital in Chicago, opened what he called a blood bank, the first institution in the United States explicitly designed to collect, type, store, and distribute blood on a systematic basis. Fantus used the term deliberately. Blood, he argued, was a resource that could be deposited in advance and withdrawn when needed, like money. The analogy was not poetic, it was operational. And in the same city, at the same time, a young researcher at the University of Chicago was beginning to investigate a question that no one had yet thought to ask seriously. Not how to store blood, but whether you needed to store blood at all. The man who solved the wrong problem, and solved it perfectly. Meet Charles Richard Drew, 32 years old in 1936, born in Washington, D.C., the son of a carpet layer and a schoolteacher. Raised in the Foggy Bottom neighborhood, graduated from Amherst College in 1926, where he was an all-conference halfback and the most valuable player in the New England Conference. He paid for medical school by coaching athletics. He did not attend an American medical school. American medical schools in the 1920s largely did not accept black applicants. Drew attended McGill University in Montreal, graduating second in his class in 1933. He returned to the United States to complete a surgical residency at Freedman's Hospital in Washington, D.C. one of the few hospitals in the country that trained black physicians. Then, in 1938, he received a Rockefeller Fellowship to study at Columbia University under a physician named John Scudder, who ran one of the most advanced blood research programs in the country. Scudder assigned Drew a research problem. The problem was not blood plasma. The problem was whole blood storage. Specifically, Scudder wanted to know whether blood could be stored longer than the existing 6 to 7 day limit. Drew solved that problem. He also solved a larger problem that Scudder had not asked him to solve. The insight came from the biology. Whole blood, the complete mixture of red cells, white cells, platelets, and plasma, breaks down because the red cells are fragile. They rupture. They release hemoglobin into the surrounding fluid. The hemoglobin breaks down into compounds that are toxic to the kidneys. The clock on stored blood was, in large part, a clock on red cell survival. But plasma, the liquid component of blood, the pale yellowish fluid that carries proteins, clotting factors, electrolytes, and albumin, does not contain red cells. It cannot carry oxygen, which is the job of the red cells, but it can do something else. It can restore blood volume. It can reverse the hemodynamic collapse of hemorrhagic shock. When a person loses massive amounts of blood, the immediate killer is not oxygen deprivation. It is the collapse of blood pressure, the failure of circulation, the shutdown of organ perfusion. Plasma, infused rapidly, can reverse that process. It buys time. It stabilizes the patient long enough for more definitive treatment. And plasma, separated from whole blood and stored under refrigeration, lasted not 6 days. It lasted weeks, possibly longer. Drew began systematic experiments. He documented the stability of separated plasma under different storage conditions, different temperatures, different anticoagulant preparations. He established protocols. He wrote his findings in a doctoral dissertation that Columbia accepted in 1940, making him the first black physician to receive a Doctor of Science in Medicine from Columbia University. The dissertation was not a theoretical exercise. By the time he submitted it, the war in Europe had already demonstrated the urgency. In the summer of 1940, France fell. Britain stood alone. The British Red Cross, facing the prospect of mass casualties from bombing and invasion, contacted American medical authorities looking for blood. The American Red Cross, in consultation with the British, designed a program called Blood for Britain. The goal was to collect plasma from American civilian donors, process it, and ship it across the Atlantic to British hospitals. The program needed a medical director. They chose Drew. He was 36 years old. He had never run a large-scale logistics operation. He had run a research laboratory. But the research laboratory had produced the protocols that the program needed, and Drew understood blood plasma better than almost anyone alive. Over the following months, Drew built a collection and processing system from scratch. Donor centers, typing protocols, separation procedures, quality control standards, shipping containers. He processed thousands of units of plasma and shipped them to Britain. The British used them. The survival rates they reported back confirmed what Drew's laboratory work had predicted. Plasma worked. But here is where the investigation takes a turn. Because while Drew was building the Blood for Britain program and demonstrating the viability of plasma at scale, a separate group of researchers, working in parallel, largely independent of Drew, was asking a different question. Not how to store plasma, but how to eliminate the need for refrigeration entirely. The answer to that question is why the German surgeon could not believe what he was holding. Stop and think about what refrigeration means in a military context. You need electricity, or ice, or both. You need vehicles to transport the refrigerated containers. You need supply chains that maintain temperature across thousands of miles of ocean, across beaches, across mountains, across deserts. Every link in that chain can fail, and when it fails, the plasma fails with it. In 1940, a group of researchers at Harvard, working under a physician named Edwin Joseph Cohn, began exploring a process called lyophilization. The word comes from the Greek for dissolution loving. The process had been described in the 1920s by a French bacteriologist named Charles Marchou, but no one had applied it systematically to blood products. The principle was simple, brutal but simple. You froze the plasma, then you pulled a vacuum and applied gentle heat. The ice in the frozen plasma sublimated, converted directly from solid to gas, bypassing the liquid phase. The water left, the proteins stayed. What remained was a dry, stable powder that contained every functional component of plasma except the water. To reconstitute it, you added sterile water, shook it, waited 30 seconds, and you had plasma. The dried product was stable at room temperature for months. It required no refrigeration. It could be packaged in a tin the size of a coffee can. It could be dropped from an aircraft, carried in a pack, stored in a tank, handed to a corporal from Macon, Georgia, who had never been inside a hospital, and administered with a 6-step printed card. Astanavis I padumaj об этом. The entire problem of blood storage, the problem that had killed men in every war since the Civil War, the problem that had defeated Napoleon's surgeons and the surgeons of the Somme, was solved by removing the water. Cohn's team published their results in 1941. The Army and Navy moved immediately. The American Red Cross, already running the plasma collection program that Drew had designed, adapted its processing pipeline. By the time the United States entered the war in December of 1941, the infrastructure for producing dried plasma at industrial scale was already being built. By 1942, the first tins were reaching combat units in North Africa. By the time of the Normandy landings in June of 1944, the Allied armies had produced and distributed over 3 million units of dried plasma. 3 million. Each tin representing one potential life held back from hemorrhagic shock long enough to reach a surgeon. Часть третья. The kit that changed the arithmetic of death. Here is what the kit looked like. Hold the image. A tin, roughly the size of a large paint can, containing the dried plasma powder. A separate glass bottle of sterile distilled water, 500 milliliters. A rubber-tipped needle set. A length of rubber tubing. A filter. A printed instruction card. Total weight, approximately 1 kilogram. Total volume, roughly the size of a hardback book. The instruction card had 6 steps. Step 1. Open the tin. Step 2. Pour the water into the tin. Step 3. Replace the lid and shake for 30 seconds. Step 4. Connect the tubing and needle. Step 5. Invert the tin and hang it above the patient. Step 6. Insert the needle into a vein. That was it. That was the entire procedure. A trained medic could complete it in under 3 minutes. An untrained man, following the card, could complete it in 5. This is the detail that German physicians found impossible, not the science, not the concept of plasma. German physicians understood plasma. They had been working with it. The Wehrmacht had a blood transfusion program. It required typed donors, refrigerated transport, and forward blood depots that were perpetually vulnerable to the same artillery and air power that was destroying everything else. The German program was logistically sophisticated. It was also brittle. Every link in the chain required another link. Whole blood required donors. Donors required typing. Typing required laboratory capacity. Laboratory capacity required rear area facilities. Rear area facilities required supply lines. Supply lines required infrastructure. And in 1943 and 44, Allied air power was systematically destroying German infrastructure. The American system had no comparable chain. The plasma was made in factories in the United States. It was shipped in tins that required no temperature control. It was distributed through the same supply channels as ammunition and rations. It sat on the same shelves. It was issued to the same soldiers. And it was administered by men with 6 steps on a card. Meet Private First Class Desmond Thomas Doss, 24 years old, from Lynchburg, Virginia. A Seventh-day Adventist who had worked in a timber yard before the war. He refused to carry a weapon on religious grounds. The army classified him as a conscientious objector and assigned him to the 307th Infantry as a combat medic. At Hacksaw Ridge on Okinawa in May of 1945, over the course of a single night, Doss lowered 75 wounded men down a 200-foot escarpment under fire, administering plasma to those in shock as he worked. 75 men, 1 medic, no surgeon, no blood bank, no refrigeration. The plasma did not save everyone. Nothing saves everyone. But of the men Doss reached in time, the survival rate was not what any previous generation of military physicians would have predicted for men with those injuries at that remove from surgical care. Doss received the Medal of Honor. He was the first conscientious objector in American history to do so. But the story of the plasma kit is not really the story of heroes. It is the story of a system. And here is the key detail. The system worked because it pushed the intervention forward. This is the concept that military physicians call the golden hour, the window of time after traumatic injury during which intervention most dramatically improves survival. Every previous system of military medicine had struggled with the same problem. The intervention was in the rear and the casualties were at the front. Moving the casualty to the intervention took time. Time was the enemy. The golden hour expired in transit. Dried plasma inverted this relationship. The intervention was now at the front. The tin was in the medic's pack, which was on the medic's back, which was within 50 meters of the casualty. The golden hour was no longer lost to transport. It was available in a tin at the point of wounding. The numbers tell the story with a precision that no description can match. In the First World War, the American Expeditionary Forces suffered roughly 256,000 battle casualties. Of those, approximately 7% died of hemorrhagic shock before reaching a surgeon. In the Second World War, with dried plasma in forward use, that figure fell to under 3%. The injury patterns were similar. The weapons were more destructive. The casualty volumes were higher. The death rate from blood loss, measured as a percentage of casualties who reached medical care, fell by more than half. That reduction, 4 percentage points across millions of casualties, represents somewhere between 60,000 and 120,000 men who would have died in the First World War and did not die in the Second. Hold that number, and then understand that the German surgeon at Polbruck in 1944 was not asking a naive question. He was asking the question of a man who understood the problem, had lived with the inadequacy of his own system's answer, and was now holding the proof that someone else had solved it better. If you followed this investigation this far and it's given you something, a clearer picture of how the problem of blood was actually solved, not the sanitized version, but the logistical, biochemical, human version, hit the like button. It helps this kind of forensic history reach more people, and if you want to follow where this goes, subscribe, because we're not finished yet. Часть 4. The verdict, what the powder actually was, and what it cost to exist. Here is the forensic verdict of this investigation. The dried plasma program was not an accident. It was not a lucky discovery made in wartime. It was the convergence of 3 independent lines of work: Drew's plasma research, Cohn's lyophilization work, and the logistical infrastructure of the American Red Cross that happens to mature at exactly the moment they were needed. The convergence was not planned, but it was not random either. It was the product of a scientific culture that had been funding blood research since the 1920s, and a military medical establishment that had studied the lessons of the First World War with unusual seriousness. Let's take each piece in turn. The science of plasma stability was Drew's contribution, but Drew did not invent plasma separation. He systematized it. He took a technique that existed in laboratory settings and documented it rigorously enough that it could be taught, scaled, and replicated by technicians without doctoral degrees. The dissertation he submitted to Columbia in 1940 is not primarily a theoretical document. It is an operations manual. It describes not just what plasma is and how it behaves, but how to collect it, how to process it, how to test it, how to store it, and how to move it. It is the blueprint for an industrial system, written by a man who understood that science is useless if it cannot be operationalized. The lyophilization, the drying, was Cohn's contribution. Cohn was not a combat physician. He was a physical chemist who had spent his career studying protein fractionation. He understood the molecular structure of blood proteins better than anyone in the world. When he turned that understanding to the problem of plasma preservation, he was not thinking about soldiers, he was thinking about the proteins. The fact that the result could be packaged in a tin and carried in a pack was, from Cohn's perspective, a consequence of the chemistry, not a goal. This is the pattern that recurs throughout the history of military technology. The most transformative solutions are almost never designed for war. They are designed for a specific scientific problem, and the military application is discovered afterward by someone with the operational imagination to see the connection. The third piece, the logistical infrastructure, is the piece that is almost never discussed. Because it is unglamorous, it involves procurement contracts, collection schedules, quality control procedures, shipping manifests, and inventory management. But without it, the science and the chemistry produce nothing that reaches a medic's pack. The American Red Cross, between 1941 and 1945, collected blood from approximately 6.5 million American civilian donors. It processed that blood into over 13 million units of plasma, of which roughly half was dried, and the remainder shipped as liquid for use in hospitals. The logistics operation that supported this was larger, in terms of personnel and throughput, than most industrial manufacturing programs of the era. And then there is the question of what the program cost to exist. Not in money, in a different currency. Charles Drew resigned from the American Red Cross blood program in April of 1941. He resigned over a policy directive that he found scientifically indefensible and personally intolerable. The American Red Cross, under pressure from the Army and Navy, had issued a directive stating that blood donated by Black Americans would be segregated from blood donated by white Americans, and that in practice, blood from black donors would not be used for white recipients. Drew called this policy what it was: scientifically baseless. Blood type is determined by antigens on the surface of red cells. Those antigens have no relationship to the racial identity of the donor. A type A blood cell from a black donor is biologically identical to a type A blood cell from a white donor. There is no scientific distinction to be made. Drew said so, explicitly and in writing, to his superiors at the Red Cross. The policy was not changed. Drew resigned. He returned to Howard University in Washington, D.C., where he became head of surgery and trained a generation of black surgeons. He published research. He built a department. He won the Spingarn Medal from the NAACP in 1944. He was elected a Fellow of the International College of Surgeons. On April 1, 1950, Drew was driving from Washington to Tuskegee, Alabama to attend a medical clinic. He fell asleep at the wheel near Burlington, North Carolina, and the car rolled. He was injured severely. He was taken to Alamance General Hospital in Burlington, where physicians attempted to save him. He died of his injuries. He was 45 years old. For decades, a story circulated, a story that appeared in newspaper columns, in civil rights literature, in oral histories, that Drew had died because Alamance General Hospital refused to treat him because he was black, and that he bled to death in a segregated waiting room. The story was powerful. It was also not true. The physicians at Alamance General treated Drew immediately. His injuries were too severe to survive. 3 of the physicians who treated him stated clearly in documented interviews that everything possible was done. The false story persisted because it was a story that fit the world that Drew had actually lived in. He had watched his own scientific work be used to build a system that then segregated the blood he had spent his career studying. The false story about his death felt true in a way that went beyond the facts. But the facts are what they are, and this investigation deals in facts. What is true, documentably, verifiably true, is that Drew built the system and then was excluded from the system's policy decisions because of his race. That is the real story. It does not need embellishment. It is damning enough without it. Перечитай эту строчку еще раз. Now. The German surgeon at Polbrook, his name does not appear in the surviving intelligence reports from that processing session. He is listed only as Luftwaffe Feldchirurg, captured February 1944, processed RAF Polbrook. He asked his question through an interpreter. The interpreter recorded it, and the record survives in the Surgeon General's archive in Washington. What he was holding was not a miracle. It was not secret technology. The chemistry of lyophilization was not classified. The principle of plasma transfusion was not unknown to German medicine. German physicians had been using plasma since the 1930s. What he could not believe was the packaging, the simplicity, the fact that a tin of powder and a card with 6 steps had replaced a chain of donors, laboratories, refrigerators, and trained technicians. What he could not believe was that the Americans had taken a hospital procedure and turned it into something a hardware store worker from Macon, Georgia, could perform at 22,000 feet. That is what he was asking about when he asked, "How is this possible?" Not the science, the operationalization. And the answer to that question, the real answer, is that it was possible because Charles Richard Drew spent 2 years in a laboratory at Columbia University, documenting every variable in plasma preparation with the rigor of a man who understood that the documentation was the product, not the plasma. The plasma already existed. The documentation made it reproducible. The reproducibility made it scalable. The scale made the tins. The tins made the 6-step card. The 6-step card made it possible for James Everett Wilder to keep another man alive in a damaged bomber over the English Channel in February of 1944. That chain, from a laboratory in New York to a tin in a cardboard box on a bulkhead in a B-17, is what the German surgeon was holding. He turned the tin over in his hands for a long time. He had good reason to. The men his forces were fighting were carrying hospitals in their packs, and the man who made that possible had been excluded from the program he built, over a policy that contradicted everything he had spent his career proving. That is the forensic verdict, not triumph, not tragedy, both simultaneously in a tin of yellow powder. Charles Richard Drew, born June 3, 1904, Washington, D.C., died April 1, 1950, Burlington, North Carolina, 45 years old. He is buried at Lincoln Memorial Cemetery in Suitland, Maryland. The blood bank he designed is still the model used by every major trauma system in the world. If this investigation gave you something, a clearer picture of what that tin actually contained and what it cost to exist, hit like. Subscribe if you want the next chapter. And remember, the most important technologies are almost never the ones that look impressive. They are the ones that fit in a pack, follow a 6-step card, and work the first time, every time, in the hands of whoever needs them most. Corporal Wilder closed the cardboard box. He hung the tin above the turret gunner and watched the drip. Outside the aircraft, the English coast was coming up. The man in front of him was alive. The powder had done what it was designed to do.